Previously, we had obtained the Maxwell equations, and I had made an argument at the time that the combination of Faraday's law and the Ampere-Maxwell law hide within them a wave equation. Now, it will be beyond the scope of this treatment for me to do a rigorous derivation of the electromagnetic wave, but I do want to at least give some flavor for the argument here. So we'll start by recognizing that at the heart of any wave equation, as we remember from mechanics, any given point in a wave has to be showing some sort of simple harmonic oscillation behavior. So to that end, what I want to note here is if we go and look at Faraday's law, this quantity here will be proportional to the electric field strength. And this quantity here is going as the time rate change the magnetic flux. So if we just look at a situation where just the magnetic field is changing and we're not changing area or angle, we can argue that this is saying that the electric field is proportional to minus dB dt. And similarly here, if we look at this term here in the Ampere-Maxwell law, again over here, this will be proportional to the magnetic field strength. So this would be saying the magnetic field strength is proportional to, and here we'll have a plus sign. And again, if we're not considering changing area or angle, the time derivative of the electric flux would be going as the time derivative of the electric field. So to argue that at least there seems to be some sort of simple harmonic oscillator type thing buried in here, and then I will use that to say, and of course that's somehow giving us an electromagnetic wave. Let's go back and at least revisit our friend the mass on a spring from mechanics. So here's a spring with spring constant K. We have a mass like so, and we pull it some distance x off of equilibrium and let her rip. So if we're out here, we're going to feel a force equal to minus kx, and this is because if we pull it to the right, x is positive, but I need the force to be pointing to the left. If I push it to the left, the force will be negative, but I need the force to point to the right. Either way, a minus sign will give me a force that points in the correct direction. So from Newton's second law, we can write F equals ma, and there'll be minus kx is ma in this case. Now let me just multiply both sides through by -1, so that I will end up with kx equals minus ma. I promise that makes some sense. Now let's follow that thought through just a little more. So here now I'm going to have, and I'll divide through by k while I'm at it. So I'll have x is equal to minus m over k. Now instead of writing a, I'm going to write the definition of a. That'll be dv dt. And then I will just plain remember the definition of v, which is dx dt. And you might look at that and say, so? But bear with me for just a second here. If we go and take a look at x here, and we look at e here, I put these both in blue boxes. They show up here, and they show up here. And if I look at b, it shows up, b and v both show up there and there. So they have the same mathematical relationship. So we're at least seeing that, yeah, in some weird sense here, the electric field is undergoing something that looks like simple harmonic motion, or at least it could. And you can make the same argument for B. We would just flip these around and do it again. So we're seeing that there's oscillations happening. Now, it's going to be a bit of a stretch here for me to basically just say, trust me, this clearly leads to it being a wave. Although I'll kind of do this retrospectively a bit, in a bit, to show that this was reasonable. Again, this is just because the treatment is beyond the scope of what we're doing here for me to be able to completely argue that we're staring at a wave. But we are. And so the prediction is that the speed of the wave, when you go and do the rigorous solution, we will at least be able to see this. The prediction is that the speed of this wave, and we'll call it c, is 1 over the square root of epsilon naught mu naught. Now, if you take the numbers and you crunch them into your calculator, you'll see that you get just a shade under 3 times 10 to the 8. 10 to the 8 meters per second, which is indeed the speed of light. Now, when workers were looking at this, they're like, wow, that's a really amazing coincidence. But they weren't willing to make the leap immediately to this being the speed of light. And it turns out retrospectively this was a reasonable thing to do, because we now know, for instance, gravity propagates at this speed. It's actually probably better to call the speed of light nature's special speed, but in our context here, and where it first showed up is with the speed of light. So historically it gets called the speed of light, but some people have proposed calling it the speed of information. Like I said, my own personal contribution is nature's special speed. Whatever. It'll show up in more than one place. Anyway, there was an experiment done by Heinrich Hertz, who eventually his name turned into the unit hertz for frequency. And what he did was he made, as I mentioned in an earlier video, he made a special LC oscillator. And then just applied charge to the capacitor to get the whole process going. And we saw that the charges slosh back and forth, making as a simple harmonic oscillator. But the big deal here is if we look at our capacitor, we will have a sinusoidally time-varying electric field. And because we're predicting that we're going to be propagating an electromagnetic wave, there should be out at some other location a time-varying electric field that can be detected. So in his original version of the detector, he basically made something that we could also schematically call a capacitor. And the electromagnetic wave propagated from here to here, and then the electric field caused charge to slosh back and forth. He had this hooked up to a very sensitive ammeter. And so, but when he looked at it, he saw that, yes, indeed, just like we predicted, the frequency that this would oscillate at would be 1 over 2 pi root LC. He saw that the needle in the ammeter was oscillating back and forth at that exact same frequency. With a lot of very careful work, he showed that the waves being transmitted from here to here did indeed travel at nature's special speed. And then in a tour de force of over a dozen papers over a few years, he showed that these Hertzian waves, as the literature was calling them at the time, they still weren't ready to call it light, because visible light was at about 1,000 times shorter wavelength than the waves he was making. He was able to show that these waves obeyed the law of reflection, the law of refraction. They interfered the same way light waves did. Basically, anything a light wave could do, he could make his Hertzian waves, which were about 10,000 times longer or so, do exactly the same thing. And eventually this got to the point where you just start to apply the duck argument. You know the one, if it waddles like a duck, and it swims like a duck, and it quacks like a duck, it's probably a duck. It's the same kind of deal. Everyone is going, okay, Heinrich, so your Hertzian waves also do this other thing that light does. And so eventually people agreed that what he did was he actually just made very long wavelength light waves. And they accepted that light was indeed an electromagnetic wave. We have now done versions of Hertz's experiment in the visible region to confirm, yes, indeed, that actually does work at those wavelengths. That is indeed what's going on. But that was that was the experimental confirmation. All right, so on the way to trying to describe these electromagnetic waves, let's talk a bit about how you generate them. So, yeah, probably without the slash. There we go. So, the general rule of thumb for how to make any light wave is you take a pile of charge and you shake it up and down. All right, so again, to do this correctly, to describe continuous motion of sloshing charges would be beyond the treatment that we could possibly do here. But I can at least heuristically argue it like this. Let's imagine that we had a single charge sitting right here. Let's make it positive just for sake of argument. We'll say it's plus Q. And we will look at the electric field lines that are emanating from it. So they will head out radially in all directions, like so. And we'll say that this is where our charge started. So I'll label this as was here. Now, what we're going to do is we are going to just somehow magically teleport our charge as a thought experiment to here. So we'll say it's teleported here. If we wait a long time, we can see what the subsequent electric field looks like, and I'll do it in, I guess, kind of a green here, just so we can tell them apart. So now the electric field lines are going to be doing something like this after they've been teleported and we've waited a long time. But what the Maxwell equations are telling us is that space isn't going to get the memo about the teleport any faster than the speed of light. So let's look at some intermediate time. So here I'll mark where the charge now is, but I'll also label where it was. Oops, by dotted line like that. And actually I'll make this even bigger here in just a sec. There we go. So here's where the charge is, here's where it was. So we'll just look at a couple of electric field lines just to get some feel for what's happening here. So out to some point, say maybe here, I'll just draw like, say, these two lines here just to get some flavor. These two electric field lines will be pointing back at our source charge. Let me take this out to the same length. All right. But this is within a circle that is as far as light would have had a chance to propagate ever since the teleportation. So anywhere inside this circle, like so, the electric field lines will be pointing at where the charge is. Now, outside here, space hasn't gotten the memo yet that the charge has moved, and so the electric field lines outside are going to be pointing at where the charge was. So say here and here. Now, the electric field lines can't just have a jump discontinuity like that. So that means that they have to have done something like this to connect the new and the old line. And you can take care of the whole sharp corners thing and stuff like that by actually physically moving the charge. But again, that's going to be beyond the scope of what we're able to treat here. But the deal is that right here we've had this huge change in direction of the electric field. So this is a change, and we will induce a magnetic field. And that induced field will be perpendicular to our change in the electric field, which is pointing like this. So the magnetic field will be oriented perpendicular to this. And then by the same token, that magnetic field perpendicular to it will be inducing something with the electric field perpendicular to it, and so forth, sending out our transverse electromagnetic wave. So that's awful hard to visualize, so fortunately, I have a way to visualize it. So in this picture here, the red lines that you see are the electric field vectors associated just purely with these points in space along the axis right here. So it's important to realize that nothing is being displaced. And the blue lines here represent the magnetic field vectors, again, at those identical locations. I can make the electric field a little more obvious here. If we look at a particular point in space, the electric field vector associated with that point in space is undergoing simple harmonic motion, which was exactly what my heuristic argument predicted. And we can see that, yes, indeed, we are propagating a wave. So this is what a typical electromagnetic wave will look like, with the electric and the magnetic fields both being at right angles to the direction of propagation. And yes, one more time, there is a right-hand rule for this. If you make the magic three-fingered widget that we've been doing for cross products, put the electric field on your right index finger, put the magnetic field on your right middle finger, and your thumb will point in the direction of propagation. So the direction of propagation is E cross B. This will actually is proportional to something called the pointing vector, which we will get into shortly in the next video, actually. So let's at least try to come up with some understanding of how, we can see that according to the computer simulation, the electric and magnetic field strengths are proportional. Obviously, it doesn't matter what the scale is here because the units are different. But they are indeed proportional. And so we can at least try to calculate the proportionality constant between the electric and magnetic field strengths. And we can also confirm that, yes, indeed, these waves are propagating at the speed of light. So I will attempt to draw a very horrendous electromagnetic wave here. We say that this is a transverse electromagnetic wave. Now, again, I can't emphasize enough that nothing is being displaced here. So this is not a wave in the same sense as a mechanical wave. It is a wave in the sense that the electric field vectors at all these points in space are doing something that mathematically looks like our mechanical waves. However, it will turn out that that's good enough, and that they act the same. It turn out that they'll have almost all the same properties, wave properties that mechanical waves did from when we studied mechanics. So I'm trying to draw this at right angles. Sorry. So let me just draw in a few right angle symbols so we're clear that yes, indeed, these things are right angles. So for instance, at this point in space right here, the electric field vector is doing that at this exact moment. But it is the electric field vector at this point in space right here. It's not saying anything about the point in space right here where we just happen to have drawn the arrow through. This entire vector arrow, remember, is just attached to this one point in space. So that's what's different. All right, so let's go ahead and label off a wavelength here. So this will be the distance from crest to crest. And this will be our velocity, which we usually use c when it's light. So if we, and then we'll also just quickly remember that the frequency of oscillation here of our electric field vector or the magnetic field vector perpendicular is going to be 1 over the period of oscillation. So with all of that, we can go ahead and say, well, it looks like we can write this down as some sort of, if we can write this down as some sort of wave, we know from mechanics what waves look like. So let's say that the electric field is going to be equal to some amplitude times the sine of 2 pi times x over lambda minus ft, which is the wave equation, and we'll ignore the phase. We'll just set the phase to be 0 at time 0. And similarly, we'll just write the exact same thing for the magnetic field, since it seems to be doing the exact same thing. Sine of 2 pi x over lambda minus f times t. This is not f of t, it's f times t. And again, we will remember here that the speed of a wave is equal to the frequency times the wavelength. So we'll take advantage of that. Now, as we're going along, I'm going to have to wave my magic wand just a little bit, and I'm sorry, but there's really no way around it. If we take Faraday's law, integral E dot ds equals minus d phi b dt, I will just assert that in a more advanced mathematical treatment, this is going to require that we can write dE dx is equal to minus dB dt. I can't really justify that here, but I can just say in a more rigorous mathematical treatment, mathematicians tell us that we can transform this to this. So what we can do is we can differentiate our guess for the electric field here. So we will say d dx of E naught sine 2 pi x over lambda minus ft. That's got to equal minus d dt of b naught sine 2 pi x over lambda minus ft. All right, and so let's go ahead and do the derivatives. So doing the derivatives here, I'm going to be left with an E naught. Derivative sign is cosine, and then this phase constant doesn't matter. there will be a 2 pi and an over lambda that come out from the derivative. So this is going to give me 2 pi over lambda E naught times the cosine of all the stuff. And here we're going to have minus. When I do the time derivative here, it's going to be the same deal. I'm going to get B naught, a 2 pi, and a minus f coming out. So this will be minus a minus 2 pi f B naught and cosine of all the stuff. All right, well, the cosines of all the stuff can cancel, and the 2 pi's can cancel, and these two minus signs can cancel each other out. And so if I rearrange this, if I times both sides through by lambda, I will get, f lambda equals, well, we recognize that that's the speed of light. And if I divide both sides through here by, we'll just leave it as f lambda equals for just a moment. If we divide both sides through by b naught, I get that this is going to be E naught over B naught. Now, with the f lambda, I can replace that with c, because the speed of any wave is the frequency times the wavelength. For the E naught over B naught, I can go back and multiply both numerator and denominator by sine of all the stuff to just be left with E over B at all times. Not just the amplitudes, but it's true actually at all times. So what we get is that the proportional that the electric field strength is equal to C times the magnetic field strength, or vice versa, the magnetic field strength is equal to E over C. So if you work that out, it turns out that typically, for typical light waves, the magnetic field is weaker than most of our instruments can detect, although we have built specialty instruments to do just that. Usually anything in practice that's observing a light wave, be it the CCD array in a camera, the retina of your eye, whatever, the rods and cones on the retina of your eye, those things are all responding to the electric field. The magnetic field doesn't really exert a big enough force on most sensor systems. All right. So now with that, let's go ahead and take our Ampere-Maxwell law and see what that can give us. So if we start with the Ampere-Maxwell law, this is B dot ds equals mu naught times I enclosed plus epsilon naught mu naught d phi e dt. And here we can set this to 0 because we're just looking at what's happening in free space, so there's an absence of currents here. All right, and then the same assertion that I made before applies here. Mathematicians have shown us that for this to be true, that's the same difference as being able to write this. dB dx is equal to epsilon naught mu naught dE dt. And so I'll just go ahead and say, make the same substitutions and take the derivatives, and I'll spare you the gory details. What you'll get after you make the substitutions and have cancel-palooza is you'll get an expression that looks like E naught over B naught is equal to 1 over epsilon naught mu naught f lambda. So now with the E naught over B naught, we just worked out that the electric and magnetic field strengths are always in proportion of ratio C. And hey, since this is a wave, this is also the speed of the wave here. So times in both sides through by C, I get C squared equals 1 over epsilon naught mu naught, or C is equal to 1 over the square root of epsilon naught mu naught, which is indeed what was predicted. Alrighty, so in the next video, we'll go ahead and take a look at the Poynting vector and radiation pressure. Catch you over there.